And now coming to our next speaker, from data to decisions, new tools and methods for sewer asset management. He's the project leader and the scientist at the Berlin Center of Competence for Water. Mathias Riechel is with us. A warm welcome also to you, Mathias, and I head over to you.
Thank you very much, Katie. Okay, I see the presentation. Thank you for the introduction. And yeah, also welcome from my side. I would now like to show you how we use the results from CCTV inspections, which was actually the core of Daniel's presentation, together with other data to make predictions on the condition of the sewer network and help utilities in decision-making. And the presentation summarizes outcomes of a project that we did in collaboration with Kompetenzzentrum Wasser Berlin and Berliner Wasserbetriebe, with many different people involved. So the starting point for setting up prediction models for the sewer network condition are the CCTV inspections and the coding of the different defects, which can be done either in a manual way, as it is the state of the art, or with help of image recognition techniques, as we just learned. And this is shown on the upper left part of the slide. Before using this data for modeling, we aggregated it on pipe level and attributed a certain condition class to each pipe, which ranges from good to very bad condition and represents a certain need for rehabilitation. And together with different deterioration factors, information on the pipes, such as the age, the material, geometric factors, and also environmental factors, such as the number of trees in the surrounding of the pipe, we can make predictions, can build models, mathematical models, and predict the condition of a network. And here we have two main focuses, two main purposes. One is a prediction on network level, a long-term prediction that helps to find good rehabilitation strategies for the network and also calculate the budget required to achieve a certain condition in the network, and a model on pipe level that identifies defect pipes or pipes with a high probability of severe defects. And this information actually can be used to support inspection programs and make them more efficient and more focused on the bad condition pipes. Before actually starting with a modeling task, of course, the first tidiest part of the work is the data preparation. And here we found major obstacle in gaps in the sewer as data, and I think this is the case for many different for many cities. In our study, in our case study in Berlin, we had 12% of the pipes without a known construction year, so unknown construction year, and that means that we couldn't calculate the age, which is the important variable for all those deterioration models. And what we did is we tested two different approaches, two different modeling techniques to predict the construction year of a pipe. One was a nearest neighbor model that looks at the construction year of the surrounding pipes of the same material and averages it to determine the missing construction year, and a random forest model, which is a machine learning model that can consider a lot of different characteristics on the sewer pipe and the environment to make a prediction. And what we see on the lower right part is a graph on the performance of both models, and both model techniques perform quite well. They have a very high accuracy, especially the nearest neighbor model, which has an error of less than 1 year for 80% of the data. This is a quite good result. The random forest performs a bit worse, but still okay. And the good thing is also that the error distribution is symmetric, so that we have both over and underestimation of the real construction year to the same extent, and all gaps can be closed. So we are able to make predictions for all pipes of the network. On that slide, I would like to remind you again of the two levels, two scales that we look at, and the two purposes of our modeling approaches. One is the network level, and for that we developed a strategy simulator a tool that can make long-term predictions on the condition of the sewer network under consideration of different investment strategies. And the second is a pipe simulator that identifies defect pipes and prioritizes them for short-term inspections and rehabilitations. And the first tool, the strategy simulator, is based on a deterioration model. That is a statistical regression model that consists in survival curves for different pipe cohorts. And the survival curve is actually what you see on the left part. It's a model that is calibrated from inspection data and determines the share of pipes in a certain condition over time, and pipes of a different of certain characteristics. So we have different groups, sanitary pipes, storm pipes of different materials, and so on. And each of them have characteristic deterioration patterns. And on the other hand, we develop different rehabilitation components, modules for renovation of a pipe. That means an inliner is put into the pipe, and a repair model that basically considers an offset on the survival curves for a delimited time. And with those two components, we can make long-term strategic planning and compare different rehabilitation strategies, which you can see on that slide. On the upper left part, we have the simulation result for a do-nothing simulation. That means that we don't do any rehabilitation. And of course, as expected, the network deteriorates over time quite significantly. So we have more than 30% of pipes in very bad condition after 100 years. And that's, of course, something that we absolutely do not want. And a way to tackle this deterioration is the renewal of pipes. As you can see on the upper right part, that's the result for 1% rehabilitation rate for the entire network per year, consisting of only renewal. And this leads to a quite good condition within a few decades. So after 60 years, we have no severe defects anymore. But this strategy would be rather costly and also has some technical limitations. We cannot renew so much at the same time in a dense city as Berlin, for example. So one alternative would be a more balanced rehabilitation strategy, which you can see on the lower left part, that consists in renewals, renovations, and repairs. And we can also achieve a quite good condition within a few decades, but there's the risk of going back to bad conditions because the renovation and the repair have a rather short lifetime. And that's the part where the user can play with the different strategies and the different shares of rehabilitation techniques to improve the condition and find a good, well-suited strategy. And the tool can also calculate the rehabilitation costs, the network age, and the value index, other important indicators for the performance of a strategy. And the pipe simulator consists of a random forest model, again, that calculates based on different pipe characteristics and environmental factors, so many different variables that describe each pipe, calculates the probability of being in a certain condition for an individual pipe. And that data, that information can be used to prioritize different areas in the city with a high probability of defects, and also find hotspots at pipe level and really find focus areas. And that model is especially good to support in inspection planning, inspection programs, in finding and pre-selecting prioritized pipes, and can find about 4 times more defect pipes than the current strategic planning, as we found in the project. So to summarize our findings, the strategy simulator can support utilities in long-term planning of efficient rehabilitation and investment strategies. The pipe simulator prioritizes pipes according to their defect probability, which allows for more efficient inspection programs. Then data gaps, for example, regarding the construction year, can be filled with reliable prediction models. And what we now plan is to also extend and transfer our results to other cities and test both tools in other places. So thank you very much for your attention. I'm looking forward to the discussion.